Hello friends, welcome back. In the last few videos, we have discussed about binary trees and the discussion about binary trees is over. And now from this video onwards, we are going to start studying about a special kind of binary tree which is known as a binary search tree. Again, this is an important topic from the examination point of view and you may get questions from this topic too. So we will start studying about binary search trees now, and I will not be explaining those topics which we have already covered in the previous videos. If you want to study those topics, then you may go back to the previous videos and can study from those videos. So in this video, we will be covering mainly three concepts about binary search trees. First of all, we will be having an introduction to binary search trees by looking at its definition, and then we will see how many number of different binary search trees are possible with n distinct keys, and then we will finally see how do we construct the binary search tree for the given sequence of values. So let us start our discussion by having a look at the definition of binary search trees. So guys, this is our definition of binary search tree. Let us have a look at it. It says binary search tree or BST is a special kind of binary tree in which every node contains smaller values only in its left subtree and only larger values in its right subtree. I think the definition is quite simple and it simply means that binary search tree is nothing but a special kind of binary tree on which we have introduced one restriction or one constraint or one condition, and that condition is that for every node the values present in its right subtree will be larger than the value of the node, and the values in the left subtree of that node will be smaller. Let us have a look at this example. This is an example of binary search tree which I have drawn for you. Now you can clearly see that this tree is an example of a binary tree because for every node there are at most two children. That is, every node of this tree is having either 0 child or 1 child or 2 children. There is no node in this tree that is having more than 2 children. So no doubt this tree is an example of a binary tree. Now this tree is also a binary search tree because it satisfies the above condition. If you consider any node of this tree, then you will find that particular node contains greater values in its right subtree and lesser values in its left subtree. For example, if we consider the node 25, this is the root node, then we will see all the values that are present in its right subtree are greater than 25. For example, 36, 30, 28, 38, 40 and 48. All these values are greater than 25 and all the values in its left subtree are lesser than 25. For example, 20, 10, 5, 12 and 22, all these are lesser than 25. Now, if you consider the node 36, then again all the values in its right subtree will be greater than 36 and all the values in its left subtree will be lesser than 36. This will be true for any node of this tree and therefore this tree is an example of a binary search tree. I hope you must have got it. Now, a question may come in your mind, what if two or more values appears to be same? Then the answer to this query is that it will never be a case because duplication of values is not allowed, and even if two values appears to be same, and that will be the rarest of the rare cases, so what you need to do, you will place the duplicate value in the left subtree of that node. For example, had there been two values 25, then you would have placed one value 25 here and then other 25 here. So you will be placing the duplicate value in the left subtree and not in the right subtree. but that will never happen because it's not possible, because duplication of values is not allowed. I hope you got the point. Now, you might be wondering why binary search trees are called by this name. Then the answer to this question lies in the biggest advantage that binary search trees offers to us. And the biggest advantage of binary search trees is that it makes the searching very faster. And the reason behind this fact is that in binary search trees, the values of nodes are arranged in a specific fashion or in specific order, as you can see on your screen, while in binary trees, there is no specific arrangement of values of nodes, and this makes the searching faster in binary search trees. For example, suppose we want to search for the value 38 in this binary search tree. Then we will start searching for the value 38 in this binary search tree starting from the root node. First of all, we will be comparing 38 with the root node value, which is here 25. And because 38 is greater than 25, so we can definitely infer that because it is a binary search tree, so if the value 38 will be present in this binary search tree, then it will definitely be found in the right subtree of value 25 and not the left subtree. Therefore, we will discard the left subtree and we will start our search in the right subtree of root node value 25. So now we will come to the right subtree of 25, and now we will find ourselves standing at the node 36. Now we will compare the value 38 with the value 36. Now we can definitely infer that because 38 is greater than 36, so if 38 is present in this BST, then it will definitely be found in its right subtree. So again we will come to the right subtree, and now we will find ourselves standing at this node of value 40, and now we will compare the value 38 with 40, and because 38 is less than 40, so we can definitely infer that if value 38 is present in this binary search tree, then it will definitely be found in the left subtree of value 40, and therefore we will come to the left subtree and we will find ourselves standing at this node. Now we will compare this value with the 38, and because both are equal, so that means this value is present in our binary search tree and the search gets over. Right? I hope you understood. Now you can think, had this tree been only a binary tree, then we would have to compare the value 38 with every node of the tree, because in binary trees there is no arrangement of the nodes, and therefore we cannot say without comparing the value 38 with each and every node of the tree that it is either present in the tree or it is not present. So this is how binary search trees makes the searching very faster, and that is the reason why it is known as binary search tree. I hope it's clear to you now. Now let us see how many number of distinct binary search trees are possible with n distinct keys. So the question is, if we are given n different keys or n different values, how many number of different binary search trees we can draw? Then the answer is given by this formula. I hope you remember this formula. We have seen this formula earlier, and this is the formula for the total number of unlabeled binary trees that we can draw for n different keys or n nodes. I hope you remember this. Now let me explain you this in the context of binary search trees with the help of an example. Guys, suppose we are given three distinct keys or three different values, then the number of unlabeled binary trees that we can draw for three distinct keys is given by 2n cn upon n plus 1, and the answer comes out to be 5. We have solved this several times. So if we consider these binary trees, consider these as unlabeled, so these will be the 5 structures or 5 binary trees that are unlabeled that you can draw with 3 distinct keys. And now suppose these 3 distinct keys are given to you as 1, 2 and 3. Now if you want to populate this unlabeled binary tree with the values 1, 2 and 3 to get a binary search tree, then there is only one particular way in which you can fill or populate this binary tree to make it a BST. Now, if you want to fill these keys in this unlabeled binary tree, then you will have to fill 1 here, 2 here and 3 here. There is no other way in which you can put these values or fill this binary tree with these values in any other way and can make it a BST. So similarly, for each structure or for each unlabeled binary tree, there is only one particular way in which you can populate that particular structure to make it a BST. And because total number of unlabeled binary trees possible are given by 2n Cn upon n plus 1, and therefore the total number of BSTs or binary search trees possible are 2n Cn upon n plus 1. I hope you have got what I am trying to explain. Guys, now let us understand how do we construct a binary search tree for a given sequence of numbers. Let us understand it with the help of one problem. Suppose the question that is given to us is construct a binary search tree or BST for the following sequence of numbers. Now you are given this sequence of numbers and you have been said that you have to insert these values in this given sequence in the binary search tree and you have to construct that BST. Now, had they been said that you can insert these values in any order, and because these are 1, 2, 3, 4, 5, 6, 7, 8, and because these are 8 distinct keys, then the number of binary search trees that would be possible will be given by 2n Cn upon n plus 1, and then you will be substituting n equal to 8 and then you will get those many number of binary search trees and the number will be quite large. But because here you are said that you have to insert these numbers in this particular sequence, then there is only one binary search tree that you can draw for this sequence of numbers. So now let us see how we will construct that particular binary search tree. So for constructing the binary search tree, we will start inserting all these numbers one by one into the BST, and we will consider the first number that is given to us as 50 as our root node. So when elements are given in a sequence, we consider the first element as the root node. So let us start inserting these numbers into the BST one by one. Please write down this sequence of numbers with you and then we will insert these numbers one by one. So guys, the first number that is given to us is 50. So first of all, we will insert 50 in our binary search tree. So you can see that I have created a node for the value 50 as our root node. Now the next number that is given to us is 70. So to insert 70, what we will do, we will first compare it with the root node. And when we compare it, we can see that 50 is less than 70. And according to the definition of binary search tree, any node contains larger values in its right subtree and smaller values in its left subtree. So because 70 is greater than 50, so we will insert 70 in the right subtree of 50. I hope you understood. So you can see that we have inserted the value 70 in the right subtree of value 50. Now the next number that we have is 60. To insert 60 in our BST, what we will do, we will first compare it with the root node, and because 60 is greater than 50, so it will definitely be present in the right subtree of value 50. So we will come to the right subtree of value 50 and we will find ourselves standing at this node, and this node contains value 70. So now we will compare 60 with the value 70, and because 60 is smaller than 70, so we will insert 60 in the left subtree of node 70. I hope you must have got it. So this is how we will insert 60 in the left subtree of node 70. I hope you must have got it. Now the next value or the next number that we have is 20. So again, to insert it, we will first compare it with the root node because 20 is lesser than 50. So we will insert number 20 in the left subtree of value 50. So now let us insert. So guys, you can see that we have inserted value 20 in the left subtree of value 50. Now the next number that we have is 90. So first of all, we will compare 90 with the value 50, and because value 50 is smaller than value 90, so 90 will definitely be present in the right subtree of value 50. Now we will come to the right subtree and will find ourselves standing at this node, and because this node contains the value 70 which is smaller than 90, so 90 will be present in the right subtree of node 70. So this is how we will insert 90 in the right subtree of node 70. I hope you must have got it. Now the next value to be inserted is 10. Again, we will start from the root node and we will compare the value 10 with the value 50, and because value 10 is smaller than value 50, so we will insert value 10 in the left subtree of value 50. So we will come to the left subtree of value 50 and will find ourselves standing at this node. This node contains the value 20 which is greater than the value 10. So value 10 will definitely be present in the left subtree of value 20. So we will insert value 10 in the left subtree of value 20. So guys, you can see that we have inserted the value 10 in the left subtree of value 20 because values in the left subtree of any node must be smaller than the value of that node. Now the next number to be inserted is 40. Now we will again compare it with the root node because 40 is smaller than 50. So it will definitely be inserted into the left subtree of value 50. So we will come here and will find ourselves standing at this node. Now we will compare 20 with 40, and because 40 is greater than 20, so it will definitely be present in the right subtree of value 20, right? So this is how we will insert the value 40 in the right subtree of value 20. Now the next value to be inserted is value 100. We will again start from the root node. We will compare 100 with the value 50, and because 100 is greater than 50, so it will definitely be present in the right subtree. So we will come to the right subtree of value 50 and will find ourselves standing at this node. Now we will compare the value of this node which is 70 with 100, and because 100 is greater than 70, so 100 will definitely be present in the right subtree of value 70. So we will come to the right subtree of value 70 and will find ourselves standing at this node. Now we will compare the value of this node with 100, and because 100 is greater than 90, so 100 will definitely be present in the right subtree of value 90. So now let us insert value 100 in the right subtree of value 90. So we have finally inserted the value 100 in the right subtree of value 90, and this is our final required binary search tree. So given any sequence of numbers in this manner, we can construct the binary search tree. I hope you must have understood. So this is a unique binary search tree, and there is no other binary search tree that is possible with the given sequence of numbers. Had the number been inserted in any arbitrary order, then the number of binary search trees possible would be given by 2n cn upon n plus 1. But if we are said that we have to follow the given sequence, then the binary search tree will be unique, and this is the required binary search tree. I hope you must have understood it very well. So guys, it was all in this video. I hope you must have understood these basics very well. Now in the next video, we will practice some of the questions that have appeared in the previous years in GATE examination. And for now, it was all. So if you have liked this video and you want us to make more videos, then please like this video and kindly share it with your classmates and friends. And also provide your feedback about how you are feeling about all these videos. And if there are any constructive feedbacks, we would definitely love to have them. And if you want these notes, you can visit the website and you will get these notes and some extra study material there on that website, which will be helpful for you in your preparation. And if you haven't subscribed the channel yet, do subscribe it now so that you can get all the latest updates. So it was all in this video. Let's meet in the next video. Goodbye.